Good morning, ladies and gentlemen. Thanks for being present. This issue comes within the Jules Always reactor under construction in France. In this project, we are particularly interested in the core vessel as it is subjected to the Spain-French order concerning the pressurized nuclear components. The welded joints are not subjected to significant flux, but they present a high risk of hot cracking, and hence the importance of the demonstration of the integrity of structure after welding. And hence the importance of the identification of the weakest metallurgical zone of fracture behavior of the welded joint to support safety assessment. For such demonstration, some of experiments and numerical analysis are required, and the strategy adopted is summed up in two main points. First of all, the identification of the local tensor behavior along the welded joints, and secondly, the identification of the toughness behavior of the different metallurgical zones. But with this, there are other parameters that must be taken into account, such as the geometry effect and the imposed loading mode that may have an impact on the analysis of the test results. I begin with presenting the studied material. So the aluminium 6061T6 was chosen for the construction of the core vessel internal structure. And the main element alloying are silicon and magnesium, which under T6 heat treatment will precipitate under inducing beta-second hardening precipitates that confers the high mechanical properties of this material. In contrast, the temperature attains during the high thermal process of welding affect the T6 heat treatment and induce, as a consequence, two other metallurgical zones, which is the heat-affected zone with significant gradient and the dissolution zone that may be divided in a fusion zone and a macroscopic interface. First of all, we have to qualify the quality of the welded joints through a coefficient which is the conventional ratio of yield stress of the base metal and a specimen across the welded joints, which give an idea of the mismatch of the welded joints. And here, as you can observe, we have a high reduction of the mechanical tensile properties by the presence of the fusion zone, which denotes of the high undermatch of the welded joints. So tensile tests were executed on specific machine equipped with two high precision laser micrometers, which are in a periodic movement during tensile tests. And as a result, we can have the profilometry of the specimen during the tensile test. Here, for example, we have the profilometry. As we can observe, first of all, the strain, the plastic strain concentrate in the fusion zone, and then it is extended to the heat-affected zone, where it remains confined until fracture. From the result of this unique tensile test across the welding joints, and without being obliged to make different tests on microflap specimens, for example, we propose to use the results to identify the local tensile behavior along the welded joints through a new processing method that was developed. The methods consist on discretizing the gauge length in endpoints and to record the true stress and strain during tensile tests, so that the local tensile behavior can be constructed at each position of the welded joints. And here, in the first approach, we compare our results, the evolution of the yield stress during the tensile, during the welded joints, with the numerical simulation of welding. And as we can see, we have a good occurrence between the two results, except in the dissolution zone, and this is due to the fact that with the numerical simulation, they don't take into account the natural aging that may occur after welding. In contrast, here we have 200 local behavior, and it is not empirically easy to implement such a model for an engineering approach. So we propose to simplify each local behavior in a set of parameters, which are the strain hardening index and the stress count index, which represent the two parameters of the Holloman hardening equation. And the differences, or finally the set of parameters, are identified along the welded joints and are seen in this figure. And one more time, we have the same tendons that we obtained later on the micro-hardness profiles. So this model will be used later for the numerical simulation of toughness tests, which will be presented in this third part. Toughness tests were conducted on conventional compact tension specimens with different position of notch radius, of mechanical notch. And here in the first approach, we compare the evolution of the effort as a function of the crack mouth opening displacement for 4 selected tests. First of all, we have the fusion zone in red. As we can see, plasticity appears at lower loads, but its high strain hardening effect delays the crack initiation. On the other hand, the base metal is hard, but the crack initiation and growth, finally we have a low level of plasticity that are involved in both crack initiation and growth. And the heat affected zone that have similar behavior to the base metal, but with the involvement of more levels of plasticity for crack extension. And this denotes, one more time, of the high undermatch in toughness as well as in tensile behavior. For quantitative evaluation or characterization of the welded joints, we propose to use the G integral. Normally, for such analysis, we are based on the ISTM standards, but it will be not easy. It will be not easy to use the ISTM as we have a multi-material effect by the presence of the fusion zone. So here, as we can observe, on the plasticity development, we have a dissymmetry of plasticity that will induce a dissymmetry of loading, and this will have no neglected impact on the eta factor linking the plastic area to the plastic component of G integral. And finally, on the G values, we have a difference of 4 kJ per square meter between standard analysis and an analysis based on numerical results, which is not neglected for this material. These correlations were developed for the different tests, and finally a model that predicts the G integral at 200 micrometers of crack extension is developed. Unlike tensile tests where the fusion zone exhibits the lowest shear stress, the integral G is enhanced and the toughness is enhanced in the fusion zone, and we have approximately 8 times higher value than the base metal. We have 110 kJ per square meter for the fusion zone and 13 kJ per square meter for the base metal. And here we have the extent of plasticity that denotes of the high undermatch between the fusion zone and the base metal that we present here. The last step is to study the transferability of this G criterion to other geometries. And here we propose to use the single-edge notch tension specimen, which represent more the rear load components on rear components. Different tests were conducted with a notch in the base metal and in the fusion zone. The crack remained in the symmetric plane. In contrast with a crack in the interface or in the heat affected zone, we have a deviation and the crackings to the softest, weakest, to the softest heat affected zone, which can be potentially the detrimental point of the welded joints. So the transferability of G at 200 micrometers will be not achieved in all cases, but at initiation, the transferability was achieved for all the tested. So to conclude on the objective of this presentation, the weakest metallurgical zone, first of all, we have to define what is meant by weakest metallurgical zone. Is that the first zone where initiation occurs, or the first metallurgical zone that induces the loss of structure integrity? And here I compare the CT specimens with the SONT specimens, and as we can observe for the non-posed displacement loading, the base metal and the heat affected zone are the two metallurgical zones that initiate at first, and clearly if the crack initiates in one of these two zones, it will induce the loss of integrity of structure, as there is a little involvement of plasticity in crack extension. In contrast, if we are placed in the second assumption, the heat affected zone will not be a detrimental point, as we have more involvement of plasticity, and it will be just a base metal which represents the weakest metallurgical zone. So finally, the identification of this weakest metallurgical zone cannot be identified for all cases, but for a given configuration. Thanks for your attention.
Thanks. Any question? Please.
Very interesting presentation. I think I'm now.
Excuse me, can I ask you to present yourself, please?
Okay, I'm Adi Memoparis from Cranfield University. How significant do you think the influence of welding residual stresses on the quantified J1C values?
This part, I'm working on it because here we verify that the G is transferable to be able to dimension a test on real components, which is the core vessel. And here the importance of the residual stress will not be neglected, and even the fusion zone, which was not a detrimental point, can be a weakest metallurgical zone finally.
Okay. Any other short question? Okay. But thank you very much.